Visible, John?
Yeah, you can go ahead.
Yeah.
Okay, good luck.
Yeah. Hello, everyone. Today we will present the paper Pyramidal Flow Matching for Efficient Video Generative Modeling. My name is Vanshik Waghela, and I am joined by John Subba. Together, we will dive into how this novel framework shapes motion dynamics for scalable and high quality video generation. We'll start with an overview of the challenges in the video generation and then introduce the solution pyramidal flow matching. We'll explore its main contributions, discuss the evaluation results, and finally, touch upon limitations and future work. Let's begin by addressing the current landscape of video generation. Existing video generation models face several key challenges. Limited temporal consistency. Many models struggle to maintain coherence between frames, resulting in flickering or mismatched content, disrupting the visual flow. Inefficient motion modeling. Traditional methods often lack the sophistication to capture the complexities of motion dynamics, leading to unrealistic or unconvincing movements. Restricted scalability, generating high quality and long duration videos demands significant computational resources, limiting the practicality of many existing models. Fragmented feature integrations. Many times, models fail to seamlessly integrate multi-scale spatial and temporal features, hindering the creation of truly realistic video synthesis. Suboptimal flow matching. This all existing techniques frequently underutilize optical flow information, missing valuable opportunities to enhance generative performance through accurate motion alignment. Consider the current state of the art like Sora from OpenAI. These models operate at full resolution throughout the generation process. This means they dedicate a considerable amount of computation to processing noisy and relatively uninformative initial frames, leading to inefficiency. This paper's approach, pyramidal flow matching, offers a more efficient alternative. Introducing pyramidal flow matching. What is pyramidal flow matching? It is a novel framework designed for efficient and high quality video generation. It utilizes hierarchical pyramidal structures to process video data with varying levels of detail, ensuring both efficiency and fidelity. Hierarch- Advanced optical flow matching techniques to capture fine grained spatial details and dynamic motion patterns, promoting realism and consistency. Ultimately, pyramidal flow matching aims to address the scalability and coherence challenges inherent in video generation by seamlessly integrating spatial and temporal information. Now, let's explain the main contributions of pyramidal flow matching. Pyramidal flow matching introduces several key innovations. Hierarchical flow matching, a core concept leveraging the power of multi resolution processing for efficiency and detail. Unified model for joint training, streamlining the training process for faster convergence and knowledge sharing across different scales, interlinked generation trajectories, ensuring smooth transitions and coherence between different pyramid stages, reducing redundancy and promoting consistency. Reduction in token count. This significantly reduces the computational burden, especially for long duration video generation, leading to faster training times and reduced resource consumption. High quality video generation, delivering visually impressive results with smooth motion, rich details, and adherence to textual prompts. Let's take a closer look at hierarchical flow matching, a cornerstone of our approach. This is a paradigm shift in video generative modeling, and it's specially designed to replicate the interplay of motion and spatial dynamics across multiple stages, delivering videos with unmatched realism and consistency. The core pillars of this method is the pyramid of precision, the flow nexus, and generative harmony. Let us now see the benefits of hierarchical flow matching. Hierarchical flow matching offers several benefits over traditional models. Reduced computational demands processes multiple solutions simultaneously, requiring full resolution only in the final stage. This contrasts with cascaded approaches that use separate models for each resolution, leading to significant computational savings. A unified model for end to end training. It utilizes a single model for all pyramid stages and enables end to end training and promotes knowledge sharing. This results in faster and more effective training compared to traditional methods reliant on separate optimization of multiple models. Significant reduction in token count. The spatial and temporal pyramid designs drastically decrease the number of tokens needed during training. This leads to reduced memory consumption and faster training times, particularly beneficial for longer videos. This figure visualizes the spatial pyramid in action. The pyramidal flow is divided into multiple stages, as we can see, each starting with a uh, pixelated noisy representation and progressively refining it towards a cleaner result, which is of high resolution quality. During inference, we strategically introduce corrective noise at the transition points between the stages. This ensures continuity in the probability path and prevents blocky artifacts, resulting in smoother and more visually appealing outputs. Unified model for joint training. This is another key advantage, you, which is provided by pyramidal flow matching. Traditional cascaded diffusion models employ separate models for different image pyramids to improve efficiency. Pyramidal flow matching proposes a unified objective that can simultaneously generate and decompress visual content across pyramid stages with a single model. Instead of relying on separate models for each pyramid, pyramidal flow matching integrates them into a single unified model for end to end optimization. This eliminates the need for each stage to regenerate from pure noise, a limitation observed in some cascaded models. Now, my friend John Suba will continue from here.
Okay, thank you, Vansik. Now I will be continuing from where my friend have left. So he was talking about unified modeling. So this method is usually required because it helps, this process helps to improve the efficiency and knowledge sharing by trying to merge this generation and decompression into a single framework. So that means what we're doing is interpolating between different noise levels and resolutions and effectively smoothing the transition between different stages of video generation and refinement. So in in my slide, what I'm about to explain is the interlinked generation trajectory. So what it does is how it introduces the interlinkness between the generation trajectories, the flow of the pyramid. So each stage is built on the output of the previous one. So this will help to ensure continuity and coherence. So you can even see in the picture, in the figure that as each stage pyramid, the generation is conditioned on the compressed and low-res history to improve training efficiency. So this is what happens in autoregressive models. So uh, this is what they are doing is that they are interpolating between different noise level and resolution. So this helps to effectively smooth the transition between the different stages of video generation and refinement. So this process generally start with noisy data, and that is at low resolution, and as the process progress, the noise is reduced and the data becomes cleaner and more detailed at higher resolution. So if this actually uses the something that the technique called as downsampling, which they reduce it by the factor of power of 2, and then they add some noise, and then after that's done, the data starts from then the data starts from highest target and then again add some noise and while downsampling it to lower resolution. So this means that we're upscaling and we're upscaling the downsample higher rates and then again adding noise. So the float trajectory would be more consistent and straight. So it eliminates the need for separate initialization at each stage and it reduces redundancy. So normally what we're doing is we're just uh, learning the actual flow function, that is some vector field, and then there is another again conditional vector field, and the difference between that uh, is then we compute the difference between that, and our main objective is to train the model to match this vector field. So we what we are doing is we are regressing into that learned vector field. So this is the flow matching main objective, and by doing this we will get our efficient model. So uh, this is the normal flow of this method, and you can easily see that it it is quite different from the normal models. Like in full sequence diffusion model, what happens is that the entire video is generated at once with all frames produced simultaneously. That means this method, these full sequence diffusion models are limited to generating videos of fixed length, but our model is quite different because it has separated the spatial pyramid, temporal pyramid, and it takes it in 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 a parallel way, just like that. So there is this concept of divided attention in other models, but unlike that, which is also called factorized attention, which is used by the prevailing models. Uh, the author of this paper has chosen to use the full sequence attention. Uh, so this is only possible because of this pyramidal representation. So in if you look at the spatial pyramid, first thing you notice is that downsampling and upsampling happens there. So it is basically about the spatial dimension, that is the reduction of the pixel value. So usually you don't need to work on full res image at the beginning. So because there is noise and doing it on full res at the beginning would add unnecessary or redundant computational complexity. So this is their technique. And then if you look at the temporal pyramid, so what it say is that it generally divides the history conditions into compressed context, and other is the same process like unified flow matching, single diffusion transformer, and we also add some Gaussian noise, and then finally there is standard transformer. So uh, this actually is one of the methods. So, and again, in autoregressive video generation, the frames are generated sequentially, one after another, which allows for flexible length generation, meaning the model can produce video of different length during inference. So this is the what do you say advantage of using autoregressive video gen model compared to other full sequence diffusion models. So it it doesn't restrict us to a fixed length. And then also, if you look into recent research, it has shown that these autoregressive methods can be very effective at generating long duration video content, and this also generate video frame by frame rather than all at once. So definitely, it is uh, one of the efficient techniques, and and if we like look into the implementation, the how does this architecture is being implemented. We I'll give you a brief um overview. Like the base model used for training starts with MMDIT architecture from ST3 medium with 2 billion parameters, and for positional encoding we use special for special dimension. Actually, we use sinusoidal positional encoding, and for temporal dimension we use like 1D rotary position embedding that allows model to support flexible training for videos of different length. And then the author also suggests the use of 3D variational autoencoder to compress videos both spatially and temporally. Like the downsampling ratio is usually 8 into 8 into 8, and the variational autoencoder is trained from scratch on wave with 10M dataset, and something similar. So and also the pyramidal stresses numbers is usually set to 3 across most of the experiment done in this paper. And for corruptive noise they have added something like uniform corruptive noise. And and this is how they have used as the experimental system. Okay, wait a minute. And when we're talking about efficiency, uh, it is already efficient, because if you like compare it to a typical full sequence diffusion setup, the video has usually T frame latents, that is encoded version of the latent, and each frame contains n tokens at the original resolution. So uh, if you do the maths, the input token would be required would be t into n, and the computational complexity would scale as the square of those, means t squared into n squared. That means every token interacts with each other token, since it is a full sequence diffusion model. But in contrast, this novel approach, or let's say this pyramidal flow matching framework, reduces the number of token, because by substantial reduction. Like it uses t into n, but we divide it by 4k, because we already said that it downsamples in a power factor of 2. So the computational complexity is reduced to, again, if we square it, it would again be there would be dramatic decrease in computation. So you can see that uh, it is like it is already using less tokens. Like just for taking example, like 10-second video at 768p video with 241 frames. A standard diffusion model takes greater than 100k tokens, but our approach takes less than 15k tokens. So that means uh, this our model is more than efficient. And if you like compare it to the computational resources like taken, so normal models like open soda, for example, they require huge hours, like 4800 SN hours and 37,000 plus hours of H100 GPU to generate only 97 video frames. In comparison to this model, it uses only like 20,000 hours of a 100 GPU hours to train 10-second video with 241 frames. That means it performs way better as compared to open soda, which uses twice the computational cost. So uh, we can see that the efficiency is far better in our case. And if you look in here, the video quality generation would take only like 56 seconds for inference, and it can also produce visually consistent and motion smooth output even for like a shorter duration, 10-second duration, something like that. So now let's move into the evaluation results. So for evaluation, we have used the two of the major benchmarks like the Vivens and Eval Crafter. So Eval Crafter. So Vivens is comprehensive benchmark for mostly video generation model. So it is evaluated on 16 dimension and Eval Crafter on 17 objective metrics. So side by side, it is compared with in Vivens, it is compared with 8 baseline models like OpenSoda Plan V 1.1, OpenSoda 1.2, VideoCrafter 2, Gen 2, Pika 2, 12V Turbo, Cog Video X, Kling, Gen 3 Alpha. And for Eval Crafter, this model is compared with 6 baseline methods like the model scope, So 1, Lavi, VideoCrafter 2, Pika 1, and Gen 2. And all the models compared are based on full sequence diffusions, and the authors of this paper argue that their approach, which combine the benefit of autoregressive generation and flow generative model, leads to better training efficiency. And there are certain evaluation metrics like visual quality, motion smoothness, semantic alignment, and also the realistic movement in videos. That is the dynamic degree. So if we look at the chart of the evaluation metrics, we can definitely say that normally Vivens is always used to evaluate the model on 5-second 768p videos at 24 fps. So wait a minute. Uh, I'm at 1 sec. Can you go to the previous slide? Vivens, yeah. And here, normally, if we look into the motion quality, this model achieves competitive result, especially for motion-related metrics. Like, for example, the dynamic degree ranks second at 64.63, showing its strong temporal dynamic learning. So, as you can also see, the quality scores is 84.74, highest among other open source competitors, and um comparing to baseline models, it performs outperforms a lot of other open source models like OpenSora and Cog Video X, especially in motion smoothness, temporal flickering, and dynamic degree. But there is also like the cons, like it underperforms in color and appearance style, likely maybe due to the video captioning method used, because it mostly use coarse grain caption that affect the image quality. And next slide, please, Vansik. Think. Okay. In Eval Crafter, we generally focus on text to vid generation, and here the model achieves higher score in various categories like the VQAA, VQAT, and Motion AC score, where it like ranks second overall. So it also demonstrates that it has strong performance in spatiotemporal pattern learning. So if you look at the final sum score, it's 244 among the top performers and 67.94 in visual quality, which is higher than Gen 2 and other open source model. That means uh, if we also look into the semantic alignment, the model perform well. This is measured by Bib Blue and Clip scores, and these are competing with closed source models like Gen 2. So, and it is something like this model is definitely has its lot of strength, but there is also a little bit of weakness in shown like seen in Eval Crafter, like it struggles in phase consistencies attributed to the design choice, maybe because of compressing historical information with a temporal pyramid. So maybe the author suggested that it can be addressed in later with improved temporal compression techniques in future work. But for now, we can definitely say that the comparative performance of this model demonstrate superior performance to several state-of-the-art model like Gen 2, Pika 1, Cog Video X, especially in motion smoothness and temporal dynamics. So this is a significant benefit in motion and semantic alignment. Maybe there are other areas for improvement in the nearby future, for example, image quality and maybe even in human action modeling. And next slide, Vansik. So we have finally come to the limitation and future work. So most of the limitations is that it relies on accurate optical flow prediction. So noisy and irregular motions can degrade performance. For example, there is also scalability challenges, and we it also struggle to capture high chaotic or maybe even unpredictable motion patterns. In case of turbulent scenes, there are also like limitations such as autoregressive limitation, that is this current model only support auto-related video generation, limiting its ability to perform like keyframe or video interpolation. And then sometimes there is subject inconsistency. Maybe while it's not prevalent issue, but subtle inconsistency in the generated subject may occur over long period, maybe due to the temporal pyramid design aimed at improving training efficiency. But this issue can be addressed by developing more advanced temporal compression method in the future. And then, of course, there is some training data constraint, like the model lacks scene transitioning learning due to maybe data filtering procedure, and which can also be overcome in by introducing a scene director model. And additionally, there is also the absence of prompt rewriting procedure, which restrict the model to handle relatively short prompts. So that means, uh, which do affect some prompts that require more complex narrative generation. But again, this is one of the research paper that has recently uh, surfaced out. So maybe in due time it will uh, like take over and manage its limitation. And in future enhancement, we could incorporate uh, even adaptive flow models for better handling of diverse motion, and it can be even optimized for real-time video generation and explore advanced data set like for improved generalization. So I think that's the last slide. So thank you everyone.
Thank you, everyone.
This is the end of the presentation. So have a great time, guys.